So we have already looked at pre-training of vision language models, which are autoregressive, and they are very good. And now we'll look at the next set of family of vision language model, which are using contrastive learning. And one of the first methods which we look at is clip and align. Okay. So these are some of the methods which we will cover, and these methods are very decent to for the zero shot and few shot learning point of view. Yeah. So if you ask these methods to generate captions, they would struggle a little bit. Yeah. And these methods will give you good zero shot segmentation, good few shot segmentation. If you have a problem, and you want to do prompting and so on and so forth, so this will be quite good for zero shot, few shot prompting, and we will discuss some of that today. Okay. So, and not so good for example, for the task of image or video captioning or visual question answering. So they would struggle. You can adopt these models to do that too. But the performance wouldn't be as good. Okay. So let's look into the first one, the clip and align. So clip is coming from OpenAI ICML 2021. I think at that time, okay, yeah. By that time, OpenAI was actually started to be a closed AI, so they stopped sharing stuff. Yeah. Okay. Before that, they were sharing everything, which was good. Okay. So let's look into this into detail. It's very simple and straightforward. So we have covered something which is called info NCE when we were discussing SimCLR, when we were discussing the contrastive learning for images. Yeah. And there what we did is that we take augmented view 1, augmented view 2, we find the cosine similarity, we did the softmax normalization, and we applied the info NCE loss. Yeah. So we are going to use info NCE here as well. Okay. So what we have here is a bunch of images and corresponding text associated with that bunch of images. We have text encoder, could be any text encoder, could be transformer, could be LSTM based, CNN based, and then LSTM based, doesn't matter much. Image encoder could be CNN, could be transformer as well. Yeah. So typically people are nowadays using transformer for image encoder and transformer for text encoder. So if you have an image encoder with CNN, you will have a feature map which is typically 7 by 7 by something. Yeah. So this is the typical feature map. So you will take the average pool of that and get 1 by 1 by whatever 1024 dimension representation. Yeah. So you will get one feature map, and that one feature map is I1. Similarly, I2 is the second representation for second, third, fourth, and all the images in the batch. So you have n images in the batch. Okay. Same for the text. So for the text, and if in the case of transformer, if it is a transformer, you will just use CLS token. Yeah. So CLS token will be your representation for the image, or you can take the average pool of the data token as well. That's fine too. Okay. So for the text part, you also take the CLS token of the text, and that gives you T1, T2, and Tn. Fine. So far so good. Good. Then what you do is that you normalize this vector, image 1 and image 2, which is not shown here, with L2 norm, and that is also standard. We did that, yeah, in the vision part also. And then you take the dot product between them. So this matrix which is shown here is the dot product essentially between image 1 and text 1. Image 1 and text 1 are positive pair, yeah, because they are the same thing. They represent the same thing. Then image 1 and text 2, and so on and so forth. So the first row here represents the similarity of image 1 with all the texts which are there in the batch, and so on and so forth. Any column here, for example this, represent the similarity of text in batch, so in the sample 3, the text of sample 3 with all the images. Yeah? And on the diagonal, what you will have always is positive pair. Good. Now what you do is two things. So you do image to text loss and text to image loss. When you are doing image to text loss, you will normalize this matrix in this way. So you need to do softmax normalization. Yeah, you need to pass it through this normalization. So when you are doing this, you normalized each row. So in the denominator, you pass the dot product through the exponent function exp, and you take all the other in that row and put it in the denominator. Yeah. So that's the relative positiveness, if you like. You take the log, take the negative of it. That's image to text matching loss. Info NCE. Just the difference is that in Info NCE, you had in SimCLR, you have view 1 and view 2. Now, one view is coming from the text. That's it, literally. Yeah, there is nothing else to it. Okay, and then when you are doing text to image, so then you normalize in this direction. So for text to image, you normalize in this direction. So you run this over the images. So this is clip. So they took, I think, 400 million weekly labeled samples from internet using line dataset, I think, and they just did that onto this 400 million image language pair. That just Info NC, and that's the training. Okay. So it's very simple and straightforward. Now, once you have trained that model, now the question comes that how would you like to use this model? So I will give the example of classification. Again, you can look into the papers and so on and so forth, and there are other stuff for segmentation and so on and so forth. So now, once you have trained your image encoder and you have trained your text encoder, you want to do classification. So what you will do is that there is an incoming image of a dog. So just to make sure it's a dog, yeah. So you pass it through image encoder, you get the representation, CLS token representation. So that's your image representation. Now you want to see whether this is an image of a plane or a car or a dog or a bird or any set of classes. You can have 100 classes, you can have 1,000 classes, you can have any number of classes, yeah. Because now this, all you are going to do is that pass this prompt a photo of a plane. In the first case, photo of a plane. In the second scenario, photo of a dog, photo of a car, photo of a dog, and photo of a bird, and so on and so forth, all of them. So this first text is the output of the text encoder representing photo of a plane, photo of a car, photo of a dog, photo of a bird. And then you do what? Normalize it and take the dot product. Wherever you get the maximum response, that's the class. And the maximum response corresponding to this is relative to photo of a dog, and then that's the label. So that's enable something which is so-called open set classification and open set detection, because you have seen 400 million samples and coming from internet, they have all kind of objects. So ImageNet is limited to, there are two scenarios, 1,000 images or 22,000 object category, either 1,000 object category with 1.2 million images, or you have 22,000 category with 14 million images. But you can't go above that easily, yeah? You can still do a lot of fancy stuff and techniques which is out of scope anyway, and you can generalize to novel object discovery, but this gives you that by default. You want to identify something, I don't know, Apple Pencil, yeah, or watch. You can do that, a photo of a watch, and it will give you that. Even if, okay, I wouldn't say that hasn't been seen. It has been seen before, yeah. 400 million images will contain a lot of stuff. Okay, okay. So I will put some of the results for this, and I will leave a lot of it for you to read and study. It's quite interesting to see and study, yeah. So they are reporting zero-shot ImageNet accuracy. So this is zero-shot. It means that you haven't taken a single sample. You have taken exactly 0 sample to train. It means you didn't train. Yeah? You can do 1 shot, you can do 2 shot, you can do 3 shot, and there are papers on few shot. Engine has quite a lot of paper on few shot learning and 0 shot learning. Some of the papers we have as well. So you can look them up, and you have covered actually 0 shot and few shot. So this is 0 shot setting, and this is the performance they are evaluating, and this is they are comparing it with respect to number of images. And you can see that as you are increasing the number of images, the performance is increasing. Yeah, common sense. So that's no surprises there. They also are showing the 0-shot performance of different models. They are comparing it with the so-called ResNet 101, and they are doing it with Clip as well. So once you have ImageNet kind of distribution, so these are the bananas which you would typically find in ImageNet, yeah, and the performance is quite good. If it is in distribution, performance is quite good for ImageNet 101, ResNet 101, and for the 0-shot Clip as well. But once you start to go out of distribution, for example, here, these are bananas which you can, as human, detect very easily. Even a child would be able to detect. Couple of year old will be able to tell that, oh, yeah, that's banana. Yeah. But you see the other models are struggling. So while the Clip is doing pretty well, and you can see that if it is more complicated, Okay, so there are some bananas here, and you can see that this banana is cut into pieces, and so on and so forth. So then then the model will start to struggle while Clip maintain decent performance. You can argue that Clip has seen all kind of data, yeah. While this guy here didn't see that much data or that kind of data, so it makes sense to have. But they were one of the first one to do it, yeah. So the paper is very famous. Okay. And of course, they evaluated it on text to text retrieval, text to image, image to text retrieval, image retrieval, text retrieval as well, and it performs very well across the scenario. They did it on other data set as well. For example, they took YouTube data set and they pass this aeroplane, and it is able to detect aeroplane, it is able to detect bird, it is able to detect quite a lot of stuff. It is able to detect this painting kind of husky image as well, and it is able to classify that more or less correctly. Okay, good. Any question on to that so far? Okay. I think shortly after this, there is also a paper, Align, which is also in ICML 2021. So I think this is coming from Google. So what they did is that they again, so it's very simple. So you have text encoder, you have image encoder, you have image text pair data, noisy from internet, and then you do contrastive learning. So let's look at the contrastive learning. So they have this image to text, text to image, or it's identical to Clip. Yeah, there is no difference. Okay, so what they did is, again, they took a lot more samples. So they took 1.8 billion vision language pair. Clip is taking 400 million vision language pair, and the rest is the same. Yeah, so yeah. Okay, so you can see that they are comparing with Clip as well, and I mean, they are using what, like around 4.5 times more data, so they are slightly better. Okay, no surprises. They changed the network as well. So they experimented with VIT. The Clip experimented with VIT and ResNet, but they experimented with a bunch of them. Okay, good.